assurance standards for 3D printed construction, a 3D printed sand wall, and microfluidic devices that can heat themselves. So the first news, which I think is an absolute wonderful piece of news, comes to us from ISO ASTM, and they've jointly released 52939 2023, which is a quality assurance minimum standard for additive construction. So this is absolutely fantastic. Also, really, really wonderful timing because we've been seeing a couple of things going wrong with 3D printed structures recently, and this is underscores the need for safety and quality assurance standard. This deals with cement, polymers, and kind of composite structures, both for commercial construction, civilian construction. The standard hopes that it's going to lead to more sustainable, durable construction methods that are perhaps eco-friendlier and faster, and that hopes to reduce the level of risk and to get better standards, better approvals, and also just better kind of like conforming to standards generally across this industry. It's not about like materials handling, that kind of stuff. It's about simulation, how you do a dry run, how to test articles and that kind of thing. So really very, very needed, and very, very welcome thing. The Museum of the Future in Dubai has unveiled a 6-meter 3D printed wall. There used to be a segment of this wall was in the museum already, but now they've extended it and put a 6-meter wall in their permanent collection. It's made by the architect Barry Wark, and essentially it's a binder jet sand structure. It's made by binder jetting. Binder jet for sand has been used by Voxajet X1 and others, mainly Voxajet X1, for sand molding kind of applications. Also, it's been used for architectural stuff as well. Voxia has done a bunch of things. Sandhelden have done a bunch of things. They made walls, room dividers, architectural kind of things, and kind of art pieces and like this technology as well. It looks really, really very cool if you've seen a large scale piece with this. What they say, this is a quote: interiors, facades, and even structural elements with technology due to its load-bearing capabilities and potential durability is what Barry Wark wants to explore. I, for one, hope that this does not happen, because whereas binder jet in its cured state in a final metal product is very, very suited for a lot of applications, binder jet uses a binding material and the sand to print and get the sand to stick together. So if this binder is not removed, then what happens is that the binder material has a different rate of cooling and heating up than the sand. And especially if it freezes, this wall is going to break. And if it kind of would heat and cool, let's say in a temperature like the desert or something like that, where it's very hot during the day and then cool during the night, we may also see problems with that. So I don't think this is ready for this kind of application. I think it's more like, at the moment, kind of a sand interior design kind of thing. I would not want this to be a load-bearing structure or that kind of thing, personally. Unless they find out how to make the binder operate and cool and expand and contract at the same rate as the sand, because that's, of course, always going to cause problems. The next thing is MIT researchers looking at microfluidics. So microfluidics have been used, made with 3D printing often. The reason for that is that 3D printing can make really intricate structures, enclosed structures often as well, because we can remove support material. And we can do that really efficiently. A lot of microfluidic devices have to be made like in a clean room, or they have to be made by hand, or a bunch of different steps, like a molding PDMS step and all this kind of stuff. So 3D printing something is always like going to be a really cost-effective option for these kind of things. Now, what the MIT team has done is they've managed to make heating elements that they can like electrically heat inside this microfluidic device. And that heating element has been able to with just $2 worth of material, right, for the whole microfluidic device, has been and less cost if they made it in a different way, has been able to heat the fluid in that device by 4 degrees. Now, what they've done is essentially in a one nozzle, one step kind of process. They have PLA, regular PLA, and they also have copper nanoparticle doped PLA. The PLA copper nanoparticles are able to deposit in these 500 micrometers small, 400 micrometers high walls, which is incredibly tiny, and they can then be heated, and unexpectedly, really, they can then heat up the liquid inside. So this is absolutely fantastic work. The team also wants to add magnets to be able to do even more. But think about these microfluidic devices becoming like less a test chamber now, or less a dosage system now, but something that's like akin to like a little micro factory that can live inside the body, or in a really small place that can test something and manufacture something. Really, that's kind of where we're headed. We seem to be headed with microfluidics, where we're really making something that is like a little mini itty bitty factory that can do a particular series of chemical reactions inside a really small space in a really discrete, really well measured way. So that's very exciting. Well, microfluidics is now, you use it for drug tests or little experiments and stuff like that. But I think this is some technology that can really be a much wider. Have much wider application areas, and we could see this coming back to us from many things if they can really iron out a bunch of the kinks. And one of the kinks is how to manufacture these things. So that would be good for 3D printing as well, if we could manufacture these very tiny, very intricate objects as well. So this is everything for today from 3D Printing News Unpeeled, brought to you by 3dprint.com. My name is Joris Peels, and I hope you have a wonderful day.